Hello everyone, we are Binary Baldness. I'm Chen Yao. Today I will introduce our project and present the role of the 4-to-1 multiplexer in our ALU project. Our project revolves around designing an arithmetic logic unit, or ALU, which is a fundamental component of a CPU. Our ALU design is based on the reduced instruction set architecture, specifically the RISC-V ISA, and the ALU will perform arithmetic and logical operations, and it is a critical part of modern computational system. Our ALU has 4 inputs, which include 4 from A and 4 from B. Each input is 4 bits and is selected using a 4-to-1 multiplexer, which is commonly known as MUX. After the selection is done by the selector bits through the multiplexer, the inputs are transmitted to a 4-bit full adder and a 4-bit full subtractor. If ALU OP equals to 1, which is the initial carry in, an operation using the 4-bit adder will be carried out. If the initial carry in is 0, an operation using the 4-bit subtractor will be done. The 4-bit output ALU out is then connected to the registers formed by a D flip-flops. It acts as a data storage element to store operands and also the result. The final bit carry-out signal C out is ignored for a cleaner operation. Now, let's move on to the role of 4-to-1 multiplexer in our project. The multiplexer is responsible for selecting inputs to be processed in the ALU. In our project, we use a total of 4 multiplexers for each operand. First, we form a 1-bit 4-to-1 MUX, and then we compile and copy it to become a 4-bit MUX. Based on the control signals S1 and also the S0, the multiplexer will select one of the 4 inputs and transmit it to the next stage. This selection process allows our ALU to handle multiple operations efficiently and ensures seamless data flow into the full adder for computation.
Hello everyone, I'm going to explain about the adder part in our ALU project. As you can see, this is our 1-bit adder design using basic logic tests. It is very easy to design as long as you can run the CAMAP and loop the CAMAP for the simplest result. If you want to know, this is our logical expressions, which is our result after we loop the CAMAP, which is S equal to A XOR B XOR C, and C out equals to A and B or C in and A XOR B. And we just simply implement the gate, follow the logical expression for the full adder design. To make it more easy to implement it, we save it as a schematic diagram. We create a schematic diagram for the 1-bit adder so we can repeatedly use it, and this is how it looks like. Okay, and then finally we design a 4-bit adder using the block schematic diagram. Like I said just now, we repeatedly use it, and if you want to know, if you want to see the logic inside the schematic diagram, it's pretty much look like this, but this is too huge and too much. It is more easy for us to look in a schematic diagram like this. So we just need to repeatedly use 4 times the adder schematic diagram, then we can get the result that we want, which is 4 S bit and 1 D out bit. So the function of this adder is to implement the function of adder and subtract, and we give the chance for user to choose whether they want to implement the add or the subtract functions. And now let's take a look for the waveform simulation of 1-bit full adder. So when my scene is equal to 1, which means my adder model will implement a add function. And right now my scene is equal to 1, so the 1 from A will add with the Cin. So 1 plus 1 equal to 1, 0. And the CL is 1 and S is equal to 0, which matches the result from the adder model. Now let's take a look at our waveform simulation for 4-bit full adder. So as you can see, when my scene is equal to 0, my adder will perform a subtraction. So 1001 from A will subtract with 0100 in 2s complement. So we need to change it into 2s complement first to perform it. Okay, and the final result will just simply be like 0101 for S, and for CL is 1. And that's all for me.
4 D flip-flops are used and combined to form a 4-bit D flip-flop to store data. In our design, D flip-flops are used to store the intermediate results of arithmetic and logic operation, in this case addition and subtraction. Since D flip-flops can store data on the edge of the clock signal, they ensure that operations are performed in a coordinated and synchronized manner to minimize the timing issues and also race conditions. This is important for sequential circuits where operations are performed in stages and results must be held temporarily before being passed to the next stage, which is the output. From the waveform simulation of the 4-bit D flip-flop, we can see that at every rising edge of the clock, data is stored.
This is the LU design after we combine all the parts. Selected data goes to the full adder for arithmetic operation. The resulting sum is stored in the D flip-flops. We will use a functional table to analyze the quarters waveform. At the first waveform, S1A equal to 1 and S0A equal to 0, input C will be selected. For S1B equal to 0 and S0B equal to 1, input F will be selected. These inputs will be fed into the 4-bit full adder to perform subtraction using the 2's complement method when Cin equal to 0. At the first positive clock edge, the operation 1011 minus 0111 is carried out, resulting in 0100 after discarding the overflow bit. It will then pass into the D flip-flop to become LU out, storing the data until the next positive clock edge. New data will be fed into the full adder for the second positive clock edge. If reset equals 0, all the data in LU out will become 0 until reset equal to 1 as deactivated. With the same selected input in the second waveform, C is now equal to 1, perform addition, coming a result 0010 after discarding the overflow bit. This data will be stored after passing the D flip-flop. In conclusion, our team successfully designed and implement an LU by integrating multiplexers, full adder, and D flip-flops. The selected data undergoes various arithmetic operations, enabling the LU to function effectively in modern computing system. We ensure accurate data storage throughout the process. This project not only underscores the importance of LU in contemporary computing, but also enhances our skill in digital circuit design. That's all from us. Thank you.